Hello everyone. Welcome back to the last and the final lecture for the class that you missed or I will miss and you all will be attending your capstone talks is the lecture on Maxwell distribution. Let me start by providing a rather brief recap for an ideal gas. If you all remember, we looked at probably in chapter 1, that the translational kinetic energy is given by 3 by 2 kBT, the average, right? The average translational energy. The average of the velocity square is given by 3 kBT over m. Note here, in the previous case, the translational energy only depends on temperature. You can clearly see there is no dependence on pressure or any other terms, right? It's only, and another factor is the Boltzmann constant. And the last one is velocity root mean square velocity, which is given by square root of average velocity of v square. And this was given as, and this is again, we have done this in the probably the first chapter, 3 kBT over m. Right? So now what is our interest? What I'm interested right now here is we want to make sure for different conditions and for a simple case, what is the average kinetic energy? Not just we always look at averages. What about a certain molecule? So let me make this more clear, right? Let's draw two containers. Let's say you have two containers of the same gas, right? Two containers of the same gas, equal number of, let's say, molecules, roughly, right? And let's say one of them is at 300 kelvins, the other one of them is at 500 kelvins. Obviously, you all know the relationship. So now you will say, well, the average kinetic energy in this case is lower when you compare to the average kinetic energy in the other case, which is higher. The point I'm trying to make here is, again, not all molecules have the same kinetic energy and as a result, same velocity, right? Think about this. Not all molecules in any of this container at a given time have the same kinetic energy. And as a result, the same velocity. It is not possible. Some could be moving faster, some could be moving slow. We don't know. We are talking about average. You're talking about average. If we needed to, someone actually pinpointed that, can you give me the velocity of this molecule? It will be really tough from these average values. What you need is a good distribution function, right? A distribution function which can actually help you to identify if a certain molecule is moving at a certain speed. In the end, what we need is a distribution. And that's what we are after right now. In this section, that's what we are after. This is pretty much a recap. You all know most of these things from what you have done so far in the class. I'm going to take off this slide. Let's start the section Maxwell speed distribution. Maxwell speed distribution. And what is the goal? Our goal is somehow also, think about this as an application of the Boltzmann factor, right? We are going to use that. Application of Boltzmann factors for understanding motion of ideal gas molecules. Again, we still have, in one of these last classes, we still got to get a better understanding of some of these things about ideal gases, right? And as I said earlier on the previous slide, we already know this. VRMS is equal to V squared, square root of V square, average velocity square, is equal to 3 kBT over m. Root mean square speed. Again, this is the average behavior. Some might be faster. I would say average behavior. Some might be faster. And I'm talking about molecules, obviously. Let's say then this value. And some might be slower. In this case, how many molecules are moving at any given speed, for example, right? Our obvious question could be how many molecules are moving at any given speed? If someone asks you that question, we don't have a direct answer to that. Or for example, what is the probability of some particular molecule? Or alternatively, a similar question that could come up is, what is the probability of some particular molecule moving at a given speed? Right? What we need actually, as I said earlier, is a distribution function, right? Think about this. Technically, the probability that a molecule is moving at any, let's say, particular given speed, v, is almost zero. Almost zero, I say. Why? The speed can vary continuously, and that, as a result, there could be infinitely many possible speeds. And therefore, each of them could have a very, very, very tiny probability of occurrence, right? Any one of them. However, some are going to be less likely, some of them will be more compared to the relative probabilities of, right? And as a result, what we need is a good distribution function. The most probable speed, we can actually draw a graph, right? We can draw a graph, plot all the relative probabilities of various speeds in a graph, and look at, wherever there is the highest, the peak in the graph, and you can actually find in proportion to that peak of that graph, right? Let's first of all put that graph together. Over here, you're looking at, as I said earlier, peak. Most probable. If you had speed V1, speed V2, right? And on this side, what is this side? This side is the relative probabilities for gas molecule to have various speeds. This is meters per second. This is almost 1 over meters per second. This is a distribution function. The idea here is, if we understand what these values are, then this is going to give us a particular window into understanding what the actual, or computing what the actual speed we're looking at is, or what the probability is at this point. In this case, what we are going to do is, If you find the area under this graph, for example, if someone asks you the speed between these two, then in between any 2 points, the area under the graph between speeds v1 and v2 equals the probability that the molecule speed is between v1 and v2. I hope you all agree with that. Literally, I'm talking about this small interval, and this could be a very tiny interval, just so that you know. I have drawn it here like this. This could be a very tiny interval. Over here, dv is the height of the graph, and the probability over here, let's write this down. Over here, the probability now, you can write this down as P between V1 to V2 is equal to V1 to V2 dV dV. Here, dV is equal to height of the graph, right? In any interval between V1 and V2, this area under the graph between any two speeds is going to be equal to the probability that that molecule is somewhere. That could be a very tiny interval, and as you bring that interval smaller and smaller, closer and closer together, you can literally pinpoint that pretty much the speed of that molecule between those two places, right? As a result, over here, we can somehow actually dV doesn't change much within the interval. It's an infinitely small interval, right? Think about that. Interval between V1 and V2 is really, really small. dV hardly changes. As a result, we can actually write this down as probability of V all the way to V plus dV is equal to dV dV. And this over here, this for you, is the distribution function Our goal now is somehow to find that function. We need to understand, because that's what exactly is going to give us the probability of finding a molecule between those two speeds, right? The function is a distribution function. Its actual value, we are not really concerned about the actual value. However, to turn dV into a probability, we must integrate over some interval v, right? We should integrate over some interval v. And the function dV, think about that. The units, it's almost 1 over meters over square. Meters over speed, right? Meters over second for the speed value. So as a result, you literally have something which number does not make sense right now. We need to somehow find a value for that function. Our goal now is to somehow bring in Boltzmann factor and also our understanding so far and calculate that, right? Our goal now is, so let me put this down as how to find dV. dV is proportional to probability of a molecule having a velocity v multiply. So think about this. There are many possibilities. We want a formula, derive a formula for this dV. And we need the Boltzmann factor. Why? Because we need to know how many total number of states are there, right? But another important quantity over there is also the 3D space. If you all remember, we looked at those velocity vectors in the past. You're talking about the same thing. The dV function is going to be given by probability of a molecule having velocity v, multiply that by the number of vectors v corresponding to speed v. This is you're looking at a 3D velocity space. And over here, probability of a molecule having velocity v, you're literally looking at the Boltzmann factor, as I said earlier. And as you know, the Boltzmann factor now can be given as e raised to minus es over kBt. 3D velocity space. This is literally the surface area of a sphere with radius v. This is like, think about this is one of the cases where all those velocity vectors are pointing towards a surface area, and what you find is this value is 4 pi v square. Let me write this down. Surface area of sphere with radius v. And here, now it's anyone's guess what is going to be the energy. We are only thinking about translation energy, just so that you know. We are only looking at translational. In this case, we are always concerned with, the energy of a particular system. In just, for this case, for an ideal gas, simply the translational energy, which is half mv square, E equal to half mv square. We are going to substitute that over there and into this equation for the energy, right? The probability of a molecule being in any given state S is proportional to the Boltzmann factor. In this case, is simply the translational kinetic energy. Let's plug that in, and what you have is in this equation later on, once I bring this everything together, we'll substitute the value of half mv square here. Why? For ideal gas, translational motion is independent of all other variables. Also, low energy states are more probable. You all know that by now. We are looking at the Boltzmann factors. You all already know that they are more probable than high energy states. Specifically at finite temperatures. Therefore, if someone has to now give us a formula or derive a formula for the distribution function, then what we have here is, therefore, d of this v is equal to c, which we are going to call it a constant of proportionality. We are not there yet, right? C times 4 pi v square e raised to minus mv square over 2 kBt. Over here, I have already substituted the half mv square. Let's block this. This is our starting point. We still need to find the constant for proportionality, just so that we are still not done yet. We need to worry about this constant so that we need a precise value for that constant, right? Let me take this slide off. So what we want? Well, we want now probability of a particle between v and v plus dv is equal to d of v dv. To determine C, fall back on our original understanding. What? All probability of finding a molecule with some speed has to be 1, right? All probability has to sum to 1. To determine C, note that total P of finding molecule at some speed must be 1. Therefore, I can actually write this down as 0 to infinity dv is equal to 1. Let's plug this value in the previous equation I wrote so that actually we can go ahead and solve that integral, get the value for C, Once I get the value for C, the previous equation that I blocked in the previous slide, we're going to put that value back in that C, and it's going to give us the distribution for different speed of different molecules in an ideal gas. All right, so let's try that now. Therefore, a little bit of math here. 1 is equal to 4 pi C integral 0 to infinity v square e raised to minus mv square over 2 kBt dV. To solve this integral, we need to make a substitution to make our life easy, right? Let x is equal to m over 2 kBt times v. Therefore, dx is going to be equal to m over 2 kBt dV. Take a look here. In the previous equation, we had the term v square and dV. You're going to substitute that. When you solve this for v and take this on the other side, when you solve this for dV, take this on the other side, you're going to bring everything in terms of x, right? Therefore, let's say v squared dV is going to be equal to 2 kBt. I have inverted this over m raised to 3 halves x squared dx. I hope this makes sense because I'm going to need this function to substitute that in there. Okay? Therefore, 1 is going to be equal to 4 pi c, substitute everything here, 2 kBt over m, 3 over 2 raised to 3 halves, 0 to infinity, x square, this v square, this term becomes x square, e raised to minus x squared dx. This is a kind of a familiar form. We are not going to again solve this integral directly. I have provided this, again, I said in the previous video, in the notes, and someone can also look at the appendix if you want to understand a little bit more. But this function, again, same thing like we did for the previous Gaussian function, does not have a, it's not easily, you can't find an antiderivative to this. You can't solve this easily again, right? Again, it cannot be anti-differentiated in terms of very simple functions, like the pure Gaussian function we had. However, the trick here is we can solve this, and the value you have for here is root pi over 4. That's the value for this equation, for this term, for the integral, right? Let's plug that in here. Think of this as a given, and this is given in appendix, I believe somewhere appendix B. And I would also say C later. For some of my one running of the whole problem to solve an integral like this in physics, I have given something in the notes, so you can see that later. Therefore, 1 is equal to C, solve this full thing, 2 pi kBt over m raised to 3 halves. This root pi over 4 that went inside, that becomes 1 plus 1 half, 3 over 2, and everything else is just, put all the numbers together. A couple of steps of algebra. C is going to be equal to invert this equation, 2 pi kBt raised to 3 halves, right? Pretty much we have the value of C now. All we gotta do now is the previous dV equation, put this value of C. Therefore, d of v is going to be equal to m over 2 pi kBt raised to 3 halves 4 pi v squared. This came from, the velocity, right? The sphere, the area of a sphere with velocity v as the radius, minus mv squared over 2 kBt. This is a very important equation. This is the famous Maxwell distribution. And this is for speeds of molecule, for speeds of molecules in ideal gas. Don't forget, this is a very important part of some of the understanding that was initially developed by the work from, obviously Maxwell. James Clerk Maxwell. But the idea is its application. It is a lot of different fields that can actually apply, or use this knowledge, right? What we can infer from some of this understanding now, let's take a look. What you can do is you can actually now plot based on this. You can plot different graphs for different speeds. You can actually look at a graph and deduce the speed for different cases, right? For instance, this could be d of v, and this could be velocity, right? Over here, if someone has given you, let's say, these three graphs, in this case, height of the curve for any value of v is always going to be proportional to the number of molecules with speed near v. Literally, peak of the curve, I would say peak of the curve represents the most probable speed, or most likely speed V max. Interesting, right? Think about this. Based on this graph, if I give you this graph and I told you which one has more temperature, let's say these are T1, T2, and T3, right? So let's call this temperature T1. This is, let's say, T3, and let's say this is T2. If I ask you which is the higher temperature, you can easily from here look at this graph and understand that as T increases, average molecular kinetic energy increases. You all will agree with that understanding, right? So peak of dV is going to shift to higher speed. As a result, if someone showed you this graph and asked you the temperatures, then you can easily claim that T3 is greater than T2 is greater than T1. I hope that makes sense to you all, right? That's all I'm trying to say here is based on some of these graphs now, you can deduce information which in the past you would not be able to. The application, I would say amazing. Rates of chemical reaction. This is in chemical engineering or chemists working on some of this stuff. Rate of chemical reactions are often temperature dependent. And you all might know this, but the most crucial reason here, and the reason is the Maxwell distribution. Certain minimum molecular speed is required a lot of times, right? Think about these reactions occurring. Do you all know about catalysts? Those catalysts which are going to make those reactions go faster or slower depending on how the interactions are. Certain minimum molecular speed are needed for that interaction to occur, just so that you know. A lot of times those catalysts are going to also help to change those things. Minimum activation energy required for reaction to occur. Rate of a reaction often depends on those activation energies, and those can really be understood well if we know the Maxwell distribution for those particles. Excuse me. So the point I'm trying to make is the understanding of this speeds of different molecules in an ideal gas is really important to understand a lot of different properties. Let me try to summarize this graph, and I would say also take a look at the book as well for this final plot that I'll make, right? It will always help you to deduce something from a given graph. Let me remove this slide. Let me draw this graph again. What you can find from here. And after this slide, whatever I post online on my courses, you will see that that slide also has that evaluation of the integral. Anyone who is interested in. I'm not saying that you all have to do that. That's not the plan here in this class. But if you want to take a look, you can always certainly understand how to solve those integrals. Almost 3 different speeds. Initially, when it's close to 0, you're looking at a parabola. And again, when it's very high, you're looking at an exponential decay over there. Peak shifts as t increases. I would say peak shifts in this direction. For Vmax, or the velocity maximum, derivative obviously is 0, right? For Vmax, derivative is 0. And 3 different speeds here that we are going to provide. Again, the reason I say to take a look at the book as well is my graphs could be probably a little bit off scale, and you don't want to mess up the understanding here. This could be Vmax, the top. Over here, the next line is going to be your average speed, which is going to be slightly higher. And then VRMS, root mean square. These 3 quantities actually govern, and you have equations now at this point for all 3 of them, right? Vmax is always given by 2, and you are going to solve a couple of these problems as a homework. You're going to derive these equations using the understanding so far in this class. Average, and this was most likely. Then you have average. What is average? Is V is equal to under root 8 kBt over M. I believe there's a pi here. I could be off. And the last one is RMS. Is equal to 3 kBt over M. You're going to try to find this in homework. I believe 6.35 and 6.36 are the 2 problems in Schroeder that you will be doing. The idea here is to understand what this graph also means, right? This will be, think about this, the Maxwell distribution falls almost as V tends to 0, and also as V tends to infinity. The average speed is always slightly larger than the most likely speed, and the RMS speed is a bit larger still. So those 3 speeds are different. This is also more intuitive, right? This is more intuitive. Think about this. To compute V, you have to literally add all possible speed weighted by their probabilities. And as a result, you will find different quantities based on this in the homework. So I would say try out those problems. There are a couple of other problems that I would like to do, but probably one problem I would do in class on Monday, and then I'll on next Thursday, and then I'll move on to other material. So I hope you all enjoy these videos. Hope they are clear. Anyone who has questions from these videos, I'm more than happy to take those questions on Thursday. I will definitely be there in class on Thursday. I believe that will be 2nd of December. I hope to see you all. Watch these 3 videos. Keep working on the homework. I'm also available if anyone needs help with the homework problems. Okay. Thank you. And I hope to see you all, which is going to be pretty much the last class of the semester on Thursday. Bye.